Hello there again. We're going to look at a simple kinematics problem, this one that was intentionally written to require a computer. We're going to solve it in the way that it was intended, which is pretty straightforward, and then we're just going to embellish it a little bit and pretend that we cannot figure out the integration time from the information given. So we're going to we're going to turn a one-dimensional problem into a two-dimensional problem and then use Python's ordinary differential equation solver to integrate the differential equations and then use the event detection routine to figure out the integration time and stop the integration at the appropriate time, and then use all the total information to get the final answer. So we've done this in bits and pieces in other videos, but I just wanted to do a simple problem that has them all together. So yeah, with that, let's get started. Okay, so let's move over to the notebook and let's make it a little bit bigger so it's easier to see. And our problem is that we have a particle that's somehow attached to a cylinder. And it's going around the cylinder with an angular speed of 0.377 radians per second. And it's not moving initially in the z direction along the cylinder axis. And then all of a sudden it undergoes some sort of acceleration that's given by this equation here. The acceleration along the z-axis is given by some constant e to the minus z. So we're given this the amplitude here, this z double dot naught term here, this amplitude of the acceleration, and we're told that the initial velocity again in the z direction is 0. And we're asked to figure out how far does it go in that z direction in the time it takes to make one rotation. So we're going to solve this in two ways. The first is the easiest way. Since the angular velocity is constant, we could just figure out how long it takes to go around the circle, and that's really easy, and that's going to be our integration time. So we're just going to have one second order differential equation to solve, and we know the termination time, it's going to be the time it takes to go around the circle one time. So we're just going to integrate that equation, and that'll be that, and we'll just figure out how far it goes. And the thing here is, all the solvers I know of solve first order differential equations, so we're going to have to change this second order differential equation into a system of two first order differential equations. And I think we've done this in the past, and it's not hard. We just use the fact that position and velocity are related by the first derivative, and the velocity and the acceleration are again first derivative of each other. So we will just do that, and that's how we will proceed here. And for the second part, I'm going to just embellish it a little by just assuming for some reason we cannot solve the time it takes to go around the circle. Maybe the angular velocity is some sort of weird function, and we can't solve it. So what we're going to do is use event detection, which is basically a root finding algorithm built into the differential equation solver. And we're going to build a system of equations that has the motion along the z-axis, the motion along that angular theta direction, and we're just going to solve the system of equations, and we're going to have the event detector figure out automatically when we've covered 2 pi radians, which is one full revolution of the circle, and stop. And hopefully these two methods give the same answer. And in reality, the second method is going to be probably the one you're going to more commonly use for real world problems where things are not always so easily calculated. So in this first cell here, I've already done the imports. We're going to need Numpy. We're going to need the first order differential equation solver, solve IVP for solve initial value problem that's in the Scipy integrate package. And we're going to pull also in the matplotlib package just to do some plotting to make sure our results agree with the intuition of the problem. So we could just plot things out and see how well things are working. Okay, so let's now just actually get started, and we'll get started with this method 1 here. So I'll just move down to this cell and begin. Okay, so the first thing we're going to need is the angular velocity, and we'll call that omega, and that's going to be equal to 0.377 seconds. And the time it takes to make one revolution is just 2 pi radians divided by that angular velocity. I'm going to call that variable underscore TF. Now we're going to need to pass in a bunch of numbers where we want to evaluate our solution. So I'm going to use the linspace command that creates a bunch of linearly spaced points from the Numpy package. So let's do that. And I'm going to call that teval for the times that we want the system evaluated at. And that's going to be equal to np.linspace 0. And we're going to go to t underscore f. And if you don't give another argument here, it just defaults to 100 points. And let's just print out tf to make sure that that's a reasonable number. So print t underscore f, and let's just run that cell. And it takes about 16 seconds, which kind of makes sense because it's moving rather slowly, and the angular speed is kind of on the slow side. So down here in this cell, we're going to actually define our system of equations. I'm just going to call this equation system. Did I spell that right? It looks right. And this is going to take our time. The first argument is going to be our time, and our second argument is going to be our position vectors. I'm just going to call that x to differentiate it from the z's and thetas and whatever. So that's that. And now this function has to return the first derivative. And before we do that, let's just define, we're going to define it in the function. You can define it in a more convenient place for real things, but let's just do it here. This a0, that's going to be the amplitude of our acceleration term, that 3 meters per second squared. That's where is it? Up here, this 3 meters per second squared. So we are going to have to return the first derivative of that. So the first derivative of the z with respect to time, which is the velocity in the z direction, and then the first derivative of the velocity in the z direction with respect to time, which is, of course, is the acceleration. And I just like to do something like this first, and that's just define x prime and have it be a zero, a vector of zeros for now. Okay, so in a new cell, one thing I don't like about the Python solvers is I prefer the way the MATLAB solvers actually work. For the Python solvers, you actually need the t-span variable, which is the time span, which gives the start and end times. So it's going to be 0 and t underscore f. And you need this in addition to the t eval if you want it at multiple points. So I find that rather inconvenient and prefer the MATLAB system of just providing a t-span, which is the equivalent of the t-eval command here. And we're also going to need the initial conditions. I'm going to call that z0. And remember, we're defining the first component as the position in the z direction. So that's going to be 0. And the velocity is going to be the second component, which initially is also 0. And now we're ready to actually calculate it. And we're going to return, the function is going to return a solution object. And we call it like solve initial value problem, solve IVP. The first argument is our function, so that's equation system, equation underscore system. The second value is the t-span. The next value is the initial conditions, and then we set t eval, and that's going to be equal to our t eval variable. So, okay, if I didn't do anything wrong, we should actually be able to run this, and well, you know me, so the odds are, yep, there's some sort of error here. So what's the problem? Where's our x prime? There's probably a typo in the function. Here we are. This should be x prime. So let's run that. Let's run that, and that works. Good. So now we can print the solution object. So let's go back up here and just actually look at what the solution object looks like. So print sol, and rerun it. So we have an object here. It has the success equals true, so it worked. It has our time t eval variable here. This is our t. And then it has the t events is none, and then it has the solution down here. Now, since we have two components, this is a matrix, and it has 2 rows and is it 2 rows and a bunch of columns, or is it the other way around? I can never remember. So let's actually print out the shape here. So let's go here, print sol.y.shape. So yeah, 2 rows, and in this case 50 columns. I guess the linspace in MATLAB, I believe, gives 100 points, and maybe the linspace in Python gives 50. I always mix up the two since I use both quite a bit. So each row is the solution for that particular variable. So the first row is going to be the position, and the second row is going to be the velocity. So let's actually just print out the answer here. So let's go back up here, and instead of this, let's get rid of that, and let's print out sol.y. So that's our solution, and we're going to print the first row, which is 0, and the last element, which is -1. And what do we need to do here? We should be good. So if I run it, syntax error, what's the problem? Oh, I see. I have the extra parentheses still here. So 39.4, call that 39.5 meters. So before moving on, let's just plot this to see if it makes any sort of sense. So what I'm going to do is create a variable called z, and that's just going to be the solution, the position solution. So the z, the first row of that solution vector. So it's sol.y row 1, and it's going to be all the columns. And I'm going to create another one called v underscore z, which is the velocity in that direction. And that's just going to be sol.y, and it's going to be the second row, which is indexed to 1, all the columns. And now I'm going to come down here and go plt.plot sol.t and our z variable, and I'm going to make this a black line, and let's just run this. So it's more or less linear except for in the beginning here. Okay, so let's just plot the velocity instead. So let's go up here and do v underscore z. Run this, and I have an error. Why do I have... Oh, I put the 2 z's in here. So here we go. Our velocity goes from 0. It increases, and plateaus. And that kind of makes sense because if we go up here and look at our equation, we have the velocity is a decaying exponential of position. So as you get farther and farther along the z-axis, the velocity, the acceleration goes to 0, and hence the velocity plateaus to a constant. So that kind of makes sense. So there we are. Let's just print out that answer. Oh, the answer is still printed out here. So this is what we're after. Cool. Now let's go on to part 2 and pretend that we can't solve this we cannot calculate that time initially. So I cleaned this up without recording it a little bit, commented out the plotting things, and just printed out the time it takes to do the revolution and the distance traveled, just so that we have a reference to check our answers for part 2. So now let's go on to part 2. So now for event detections, we can tell the solver to look at a specific function that's essentially a root finding problem. So we're going to create a function that has a form g that's a function of t and x is equal to 0. Remember, x is a vector valued function. In our case up here, where's the function defined? X has 2 dimensions, and we're about to define a version that has three dimensions. So you can have multiple cutoff criteria. For example, in my day-to-day job, I do a lot of electrical and thermal simulations, and some of these cutoff functions may look at, say, a battery voltage and cutoff, and return out of the function if the voltage reaches a certain level or the temperature reaches a certain level. So these functions can be pretty involved. But for our case, it's going to be pretty simple. We are just going to integrate, as part of our differential equations, the angular velocity as a function of time to get theta, the angular position, and then we're going to tell the solver to cut off when theta is equal to 2 pi. So before going on and defining the events, let's define our system of equations first. So just as before, we're going to define a function, and we're going to call it equation system 2. And it's also going to have the same type of arguments. It's going to take t and x. And again, we're going to have to pass in this a naught is equal to 3. And now x prime is going to be equal to np.0, zeros, yes. And that's going to be have three dimensions this time. And before I forget to return, as I often do since I use MATLAB more than Python, let's return x prime. And now let's define our system of equations. So the first two are just going to be the same as our function up here. So we could just do a copy and paste job. Copy, paste, and now x prime 3, our third dimension is going to be the angular position. So x prime 2, I'm sorry, the third component, and then of course Python indexes from 0. So x prime 2. So the derivative of the position is the angular velocity, and that's just our omega value, so omega. And that in principle should do it. So let's set up the solver now. Actually, before going on to setting up the solver, we need to set up the our event function. So let's define a function called cutoff. That's going to take t and x. And I also need a colon up here, don't I? So we are just going to return. So we want some function that is equal to 0. So when our theta value, when this function is 0, our solver cuts off. So when x2, which is our theta value, minus np dot pi, it's 2 pi, it's 1 revolution, is equal to 0, this will cut off. So this just returns this value, theta minus 2 pi. And when this crosses 0, we will end our simulation. So now we go down here and we have cutoff. We want it to actually terminate. So cutoff dot terminate is equal to true. Or is it terminal? I have to check. Hold on. It's terminal. No. So cutoff.terminal is equal to true. So let's just run this cell to see if there are any issues. There are no typos, at least. Okay, now let's set up our solver. So we're going to create a new t eval variable, and that's going to be np.lin. Oh, I can't type today. Lin space 0. We don't know when this thing is going to terminate. So let's just go to 100 seconds at first. And let's have 200 points this time, just to make the density of points a little higher. So that's good. Our t-span is going to start at 0, and let's just end it at 100 seconds. So we could just type in 100 here, or yeah, let's just type in 100, or you could just like do the t-eval, the last element of that vector. So our initial conditions, let's call that z naught again. I think that's what I called it originally. That's going to be 0, 0. And now we're going to call our solver routine. And let's see, I'm just going to copy and paste from above. So this has to change from equation system to equation systems 2. And now we need to add in the event command. Event equals cutoff. So in principle, if there are no typos or no errors, this should just run. Let's see. Of course, there are errors. And it looks just like I can't even copy and paste, let alone type. Let's see. Still an error. What do we have? Oh, we have to have the initial angular position too. Remember that our vector of this going into the solver has 3 dimensions now. The z position, the z velocity, and the angular position. So we're going to start that at theta equals to 0. So that runs. So now let's see. Let's print out the solutions and see what we get here. Let's go back up here. Print sol. So here we go. Let's see. Success true. Our time values. We don't hit our event. And it took me a moment to track down the issue here. This needs to be events, not event. Go. So now hopefully we have a T event. And it looks like we do. Where is it? Here we go. 16.66 seconds. Where did we end before? Let's go back up here. 16.66 seconds. Now you notice that these numbers are slightly different from each other. And that's probably because a lot of these root finding algorithms that are built into these solvers just look for a crossing of 0, and then when one point is on the other side of 0, it just interpolates linearly between the two to get that point. So you have to be a little bit careful with that. That's kind of why I bumped up the number of density of points here. So let's just print out our final answer to make sure that we're correct here. So we want the solution.y, and we want the first row, and we want the last element of that. So that looks good. Run, and we get 39.27, and what do we get back up here? We got 39.42. And that's probably because of the interpolation. So if we were to actually bump this up to 2000, we get an answer closer to what we get above. So yeah, that's about all there is to it. So yeah, that's about it. I find I generally prefer MATLAB's differential equation solvers to Python's default solvers. At some point I should do a video exploring different Python solvers, and maybe even do a video about the differences between MATLAB and Python, and the things I like about each of the languages, and the things that screw me up going back and forth between each language. But yeah, that's for another video at a later date. So until next time, see you guys later.